Today we introduce the nondeterministic finite automaton. We're going to use the subset construction to show that every language that can be recognized by any nondeterministic finite automaton is still a regular language, in that it can be also recognized by a deterministic finite automaton. We're then going to add something to the nondeterministic automaton called epsilon transitions that allow sort of spontaneous jumps from state to state, and we will in fact show that these automata, even though they look more powerful, also can recognize only the regular languages. A nondeterministic automaton has the ability to be in several states at once. A transition in a nondeterministic automaton is from some state, say Q, on an input, say A, it can go to several different states. So we can have several transitions all labeled A. And this is the thing that allows the automaton to, in a sense, guess, to be nondeterministic. It can go from state Q to really any of these states, and therefore it actually goes to all of those states at once. Okay, like the DFA, a nondeterministic finite automaton, or NFA as we will call it, has one start state where a computation begins. The NFA can have any number of final states, and an input is accepted if any sequence of choices leads from the start state to some final state. The intuition is that the NFA is allowed to guess which way to go, but it is able always to guess right, since all the guesses are followed in parallel, and the NFA gets credit for the right guesses, no matter how many wrong guesses it also makes. In our example of a nondeterministic finite automaton, the states are squares of a chessboard. In general, you can occupy several different squares at a time. In a red move, which we represent by the input symbol R, you get to move to any adjacent red square. So in effect, you replicate yourself and move to all of them. Similarly, if the input is B, you can move to any adjacent black square. So in effect, you move to all the black squares. The question we ask is whether the given sequence of R and B inputs can get you from the start state, which will be the upper left corner, to the one final state, which is the lower right corner. The answer is yes, if any sequence of choices we get with each input leads us from the upper left to the lower right. It is not necessary that all such choices do, and in general there will always be some choices that lead us astray. Okay, so here's our example. The chessboard will be rather tiny. It's only 3 by 3 instead of 8 by 8, but the ideas are all the same. Okay. Now, using the moves which I have summarized in a transition table, but which follow the intuition that I gave you, we're going to examine the sequence of inputs RBB. That is one red move followed by two black moves. We'll start in the start state, state 1 only. So we're going to show state 1 there. Okay. Now, we get an R input, so we can move to any of the red squares adjacent to square 1, or in terms of the transition table, here's the row for state 1. We look under R, and we find states 2 and 4 are the possible moves. Okay, and notice that adjacent really means one king move, so that from state 1, let's say you can go to 2, 4, or 5, obviously only 2 and 4 on a red move and only 5 on a black move. Okay, so after reading the R, we go from state 1 to states 2 and 4. Okay, so now we're in states 2 and 4, and B comes in. So what do? Well, from state 2, We can go to 1, 3, or 5. You can figure that out either by noticing that 1, 3, and 5 are the adjacent black squares, or you can just look it up on the table here. Here in row 2, the black moves are 1, 3, and 5. Now how about state 4? Well, from 4 you can go to 1, 5, or 7 on a black move. Some of those states were already listed, but the point is that between 2 and 4, the states you can get to are 1, 3, 5, and 7. Now, that's all for the first B. Now the second B comes in, and from 1, you can only go to 5. From 3, same thing, you can only go to 5 on a black move. Now from 5, you can go to a lot of states. You can go to 1, 3, 7, and 9. And from 7, again, you only go to 5. So after reading the RBB, you are in fact, all the odd-numbered states, or actually all the black squares. Since 9 is the accepting state, we say that RBB is accepted by this automaton. The fact that it's also in states 5, 1, 3, and 7 are not relevant to the question of whether it's accepted or not. Here are the components of an NFA. They look exactly the same as for the DFA and will typically use the same letters to represent them. The big difference is in the type of the transition function, and we'll see that on the next slide. For the NFA, delta of state Q and input A is now a set of states, possibly empty, rather than a single state as it was for the DFA. The extension of delta to strings is a bit more complex. The basis is still easy. Delta of Q and the empty string is just the set containing Q, since the only state you can reach on no input is the state you are in. For the induction, suppose we start in state Q and we read string W followed by symbol A. We first compute delta of Q and W, the set of states you get from Q by following W. So let's, from Q, let's say following paths labeled W, we might get to states P1, P2, and so on. Okay, then for each of these states, say P1, P2, and so on, we're going to use the given delta function to find the set of states they each get to on A. So let's say P1 might go to these two states, I don't know their names, but P2 might also go to that one, and several others, and so on. You find all the states you can get to, but always on transition labeled A. And the resulting union, this set, is delta of Q and WA. Okay, the language of a non-deterministic automaton is simply the set of strings that it accepts, that is, the set of strings W such that when you compute delta of Q, Q0 and W, that Q0 is of course the start state, when you compute delta of Q0 and W, you have a set that contains at least one final state. Okay, the language of the non-deterministic automaton that we designed to represent moves on a chessboard is actually quite tricky to describe. For strings consisting only of B's, it's easy. You start in only in the state 1, and on the next move with B, you only go to state 5, so you're only in the set containing 5. Another B, if you'll notice, will take you from 5 to 1, 3, 7, and 9. So now, after the second B, you're in 1, 3, 7, and 9 only. The next B, well, each of 1, 3, 7, and 9 only have B as an adjacent black square. Their other adjacent squares are red. So after 1, 3, 7, 9, you are now in just the set 5. And from 5, you go to 1, 3, 7, 9, and so on. As a result, you accept all the even length non-empty strings, that is BB, BBBB, 6Bs, 8Bs, and so on. And you don't accept strings B or BBB, and so on, the odd length strings. Okay. It's less clear what happens when there are R's in the input. Obviously, an accepted string must end in B because only state 9 is accepting, and you only get there on a B move. But I'll leave it to you to figure out exactly what strings with one or more R's are accepted. Okay. In a sense, a DFA is an NFA that just doesn't have any non-determinism. Formally, given a DFA with a transition function, which we'll call delta sub D, you can create an NFA with the same states and inputs as the DFA and the same start and final states. The only thing different about the NFA is that the form of its transition function is what it has to be for an NFA. It gives you a set of states rather than a single state. But that set of states in delta n will be exactly the one state that delta D gives you for a given Q and input A. As a result, the NFA, after reading some sequence of inputs, is in the set of states that's always a singleton. It always contains only the one state that the DFA is in. Okay, so that says any language accepted by a DFA can be accepted by some NFA, and in fact the NFA really looks the same as the DFA, and it almost is the DFA. Okay. Surprisingly, for any NFA, there's a DFA that accepts exactly the same language. And the proof is called the subset construction. And this construction was the thing that, as a graduate student, convinced me that there was something to computer science theory. It had only been discovered 5 years before, and it boggled my mind to see a construction that, while it could be described easily, resulted in something that could not be grasped. Okay. The problem is that the number of states of the DFA that you get from an NFA can be the number can be exponential in the number of NFA states. Now, if the NFA has 3 states, the DFA can have 8 states. That's not a big deal. I can visualize an 8-state automaton. But if the NFA has 10 states, the DFA could have 1,000 states, and that's already becoming quite hard to imagine. And if the NFA has 20 states, which is still something we can visualize, the DFA can have 1,000,000 states, and we're completely lost, even though we know the DFA exists. Oh, and by the way, the situation is not nearly as bad in practice as it looks in theory. Many of the non-deterministic automata that you construct in things like compiler design, when you convert them to a DFA, the number of states doesn't really grow much at all, if at all. In fact, the chess NFA that we just introduced actually has an equivalent DFA with fewer states, as we shall soon see. So let's start with a typical NFA. It has the conventional names for the components, although we'll use delta n for its transition function to distinguish it from delta d, which will be the transition function for the equivalent DFA that we're going to construct. Now, in the DFA, states are represented by 2 to the q, which is 2 to the q is a mathematical notation for the power set of q, that is the set of all subsets of q. Okay. Notice that if a set q has n elements, then its power set has 2 to the n elements, so the notation sort of makes sense. Okay. So the important point to remember is that the DFA states are actually sets of states of the NFA, and there can be an exponential number of them compared with the number of states in the NA. The inputs of the DFA are the same as the inputs of the NFA. That's the set sigma. The start state of the DFA is the set containing the start state of the NFA. Okay. remember that the states of the deterministic automaton are sets of states of the non-deterministic automaton. Okay, thus the start state, which is a single state of the DFA, is written as a set of states of the NFA. Of course, this set contains only the start state of the NFA. Okay. Then the final states of the DFA are all those states that, they're thought of as sets of states of the NFA, contain a member of F. Remember, F is the set of final states for the NFA. Just to make sure we understand what's going on, the DFA states have names that look like sets of states. However, they are single objects. Okay. An analogy that might be useful to make is with a class of objects in a language like Java or C++, whose values happen to be sets of objects from some other class. Okay. The transition function delta D is defined by delta D applied to, now again, this is not a set of, this is a set of NFA states, but this is a single state of the DFA, and input A is the union over all all the states Q1 through Qk of what you get when you take the delta n, or there's the transition function of the non-deterministic automaton, and apply it to that Qi and A. So you have Q, here's Q1, here's Q2, and you see where you get to on A, and like that, that's A, and so on. And this set of NFA states is the name of the DFA state that you get to when you go from this state of the DFA on input A to the next state of the DFA. Okay, we're going to, as an example of the subset construction, do a lazy construction of DFA states. That's generally much better than assuming we need all the subsets of NFA states. Okay, we're going to start. Of course, we know we need the set containing the initial state, so we surely need, as one of the DFA states, the set containing 1, because that's the initial state of the NFA. But we're only going to create rows for states when we are sure that we need them. Okay, so obviously we need the start state of the DFA, which is the set containing 1. So we'll begin the construction with a row for the set containing 1. Now, from the NFA table, which I've outlined here in red, we know that on R, 1 goes to 2, 4, and on B it goes to 5. And since this set is a singleton, that's all we need to know. So we know immediately that in the DFA, the set containing 1 goes to the set containing 2, 4 on R, and the set containing 5 on B. Now, I've put these two sets, made rows for them in the table. I haven't filled out the rows yet, but we know that we're going to have to, because they obviously are states that you can reach from the start state of the DFA. Okay, here we've filled out the row for the DFA state whose name is set containing 2, 4. Okay. Well, on input R, we look at this is the NFA table. We look at the things marked in red, that is, on 2, so from 2 on inputs R, you go to 4 and 6, and from state 4 on input R, you go to 2 and 8. So from the set containing 2, 4 on R, you go to 2, 4, 6, 8. Again, this is a single state of the DFA. And since I haven't encountered this state before, I now create a row for it, reminding me that I'm going to have to figure out what its transitions are sometime in the future. Let's see, again, from state 2, 4 on input B, you just look at where the NFA goes on those two states, and you take the union of 135 and 157. That's 1357, and that's in there. And I also put it here because I'm going to have to figure out its row in a minute. Now we fill out the row for 5. Again, that's fairly easy. You just look at the row for 5 on the NFA table, and you enter the states right there. 2, 4, 6, 8 we've seen already, so we don't have to create a row for it. 1, 3, 7, 9 has not been created, so we will create it now. And I've also started, because notice that is a final state of the DFA. It has the final state of the NFA, state 9. Okay, now for 2, 4, 6, 8, again, I've in the NFA table, I've put in red the relevant rows. For R, I just take the union. I've got 4, 6, 2, 8, 2, 8, 4, 6, so the union is 2, 4, 6, 8. That's a state I've seen already, not interesting. On B, I've got 1, 3, 5. I've got 1, 5, 7. I've got 3, 5, 9, 5, 7, 9. The union of that is 1, 3, 5, 7, 9. That's a new state, so I add it to the list of rows I need to construct. And by the way, it's also a final state because it contains 9. Okay, here's the row for 1, 3, 5, 7. Again, the same process. You again get 2, 4, 6, 8 on R, and now you get 1, 3, 5, 7, 9 on B, and these are both states you've seen, so we add no new rows. For 1, 3, 7, 9, we just compute its entries. Perhaps the only interesting thing is that on a B, all of 1, 3, 7, and 9 go to only B. It's only 5 on B. So what you get is the set containing only 5. That is a state that we've seen before, as of course is 2, 4, 6, 8. So we don't have to add any new states. And finally, 1, 3, 5, 7, 9 also yields no new states. And so we now have completed the entire transition table for the DFA. Notice it only has 7 states, while the NFA had 9. So it actually shrunk the number of states. Again, you have to be rather lucky to do that, but it does happen. We're going to prove that the NFA and the DFA we construct by the subset construction are equivalent. That is, they define the same language. We must thus show that if one accepts a string W, if and only if the other does. That is, the two languages are each contained in the other, and therefore they are the same. Now, notice that delta n is a set of NFA states. Delta D, on the other hand, is a single state, but its name is a set of NFA states. So it is quite reasonable, at least it's an interesting pun, to argue that this as a single state is the same as that as a set of states. For the basis, let W be the empty string. Then delta n of Q0 and the empty string is the set containing Q0 by the basis rule for extending the delta for non-deterministic automata. And delta D of the set containing Q0 and the empty string is the set containing Q0, again, by the extended delta rule for deterministic automata. For the inductive step, we'll assume the inductive hypothesis that the states of the DFA, that the DFA and the NFA get to on string W are the same sets for all strings shorter than W, and we'll prove the statement for W itself. Okay. W is of length at least 1, so we can write it as string X followed by symbol A. And we can assume the inductive hypothesis holds for X, because it is clearly shorter than W. That is, we're going to assume that delta n of Q0 and X is delta D of the set containing Q0 and X, and we'll call that set S. Let T be the set of states the NFA can get to by starting in state S and following a transition on A. So that is, we have, let us say, here's set S of states, and coming out of various of these states are transitions on A. Okay, by the rule for the extended delta for NFAs, the set T of all the states that you get to is delta n of Q0 and W. By the subset construction, we also know that delta D of S and A is T. Thus, delta n of Q0 and W and delta D of Q0 and W are both T. The latter, of course, is by the extension rule for deterministic automata. That is how you compute the extended delta. So we have therefore proved the inductive step. Okay. We are now going to add an additional capability to NFAs, the ability to make a spontaneous transition on epsilon, that is, without using any input. We just saw that the NFA, while it can be a convenience in designing automata, still accepts only regular languages. The same is true for the new model, which we'll call epsilon NFAs, but they can be a real convenience in constructing automata, and yet they still accept only the regular languages. Here's an example of an epsilon NFA. The transition diagram has some arcs labeled epsilon, and we can follow any such arc without adding to the sequence of inputs that the automaton has processed. That is, epsilon is invisible as far as input strings are concerned. Okay. We also see the transition table for this automaton. Notice it has a separate column for epsilon, but epsilon is not an input symbol. It's not a member of the input alphabet. For example, from the start state A, let's look at A, there is only one transition on 0 to E, and that's why you have set containing E over here. There's only one transition, that's to B, on input 1, so that's why you have set containing B there. And there are no transitions out on the empty string. So we have the empty set symbol represents the transitions from A on epsilon. It's not an input. It represents spontaneous transitions. Let's look at E now. On 0, there's a transition to F, and only to F, so you get set containing F. There are no transitions at all from E on a 1, so you get the empty set. Okay. And on epsilon, you have transitions to both B and C, so that you have set containing BC at that entry. Okay. Notice that if we are in state E and the input is 1, then we can spontaneously go to B on epsilon, and then on the 1 wind up in C. Okay. We can also go spontaneously from E to C on epsilon and wind up in D on input 1. Okay, now to do the conversion of epsilon NFAs to regular or ordinary NFAs, we need to have the notion of the closure. The closure of a state Q, which we're going to write as CL of Q, is the set of states we can get to starting in Q and following only epsilon transitions. So, for example, from A, you can get nowhere else on epsilon, right? If you're here, there are no epsilon transitions out. As a result, the closure of A is just the set containing A. Of course, you're in A to begin with, so you can stay in A. So closure of a state always contains at least itself. The closure of E is trickier. Okay, we start in E. Surely we can reach E. Then there are epsilon transitions from E to B and C, so we can surely get to B and C. But now we have to see where can we get to from B and C. Well, C doesn't have any epsilon transitions out, so we can't get anywhere else. But B also has D, a transition on epsilon to D. D has nowhere else to go on epsilon. So the conclusion is that the closure of E on is all of B, C, D, and E. Okay, and that's what we've written here. Then we also are going to need to apply the closure operator to sets of states, and the definition is quite simple. The closure of a set of states is just the union of the closures of each of those states. Now, we need to describe the operation of an epsilon NFA by defining the extended delta. And again, it's intended to tell us about where we can get from a given state following a path labeled by a certain string W. However, epsilon, the empty string, is invisible along paths, so W only involves the real input symbols of the automaton. As a result, we follow paths that are labeled by real symbols of W, but with arcs labeled epsilon interspersed as much as we like. Okay, so for the epsilon NFA, delta hat of QA is not the same as delta of Q and A, because delta of Q and A does not include any epsilon transitions. So we're going to keep the hats on the extended delta when we need them. Okay. So for the basis, delta hat of Q and epsilon is the closure of the state Q. So it's not just Q. If you can reach anywhere from Q on epsilon, then that's included in the closure and therefore in the delta hat. For the induction, suppose the input is string X followed by symbol A. Start by figuring out what delta hat of Q0 and X is. Say it is a set of states S. Okay. For example, let's suppose that X is BC. Then we might start from Q0 and we'll follow paths labeled epsilon and then a B, and then maybe more epsilons, possibly none, to a state where we follow a C, and maybe even then more epsilons. Now, suppose this takes us to a set of states S. To compute delta hat of Q and X followed by A, we look at all the states in S, we find all the A transitions, no epsilons now. We then have to take the closure of these states, that is, we follow all the epsilon paths. And finally get to the state that is this set of states is delta hat of Q and XA. Here is an example. This is the automaton that we've been playing with. I say delta hat of A and epsilon is the closure of A. That's the basis rule. And that's just set containing A, because A doesn't get you anywhere on epsilon. Now, I'd say the delta hat of A and 0 is the closure of E, which is B, C, D, and E, as we discussed earlier. Why closure of E? Because when we already determined that the closure of A is A, and on 0, the only place you can get to from A on a 0 is E. So we have to close E. Now, delta hat of A and the string 0, 1, I claim is closure of C and D, which actually is just C and D. Why is it closure of CD? Well, look, we already know that delta hat of A and 0 is the set containing B, C, D, and E. Okay, so we're sort of here, 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 and here. Now, on a 1, where can I go from any of those states? Well, from E, no place. From D, no place. From B to C, and from C to D. So the only places you can get to from B, C, D, and E on a 1 are C and D. So that's why we start with C and D. We take the closure. Now, neither C nor D have any epsilon transitions out, so we conclude that delta hat of A and 0, 1 is set containing CD. What that means is, if you look at, starting in A, all the paths labeled 0, 1, with as many epsilons as you wish thrown in the middle, those paths lead you only to C and D. That is, there's this, there's this, and there is this. Okay, and that's it. Okay. Finally, the language of an epsilon NFA is defined in the expected way. For any string W, you compute the extended delta of the start state and that string W. And if you see if any of the resulting set of states is a final state, you accept W if so, and if not, then not. Okay, we now want to show that the NFA and epsilon NFA models yield the same languages, the regular languages, of course. One direction is easy, since an ordinary NFA is an epsilon NFA that happens to have no transitions on epsilon. But proving that for every epsilon NFA there is an ordinary NFA that accepts the same language, we're going to have to get rid of the epsilon transitions. We do that by combining them with the next transition on a real input. Okay. If you're following the text, you should notice that this construction is somewhat different from the one in the text, but both constructions work. Here, we'll have to change the set of final states, while the one in the book doesn't, but this construction is, I believe, a bit simpler. Okay. This is a picture of how we iron out the epsilon transitions. We start from a state, okay, here, and we follow all the epsilons we can using the closure operator, and I'm sort of imagining that the yellow area represents paths that are labeled only by epsilons. We then follow all the transitions from any of the states we reach on a real input symbol A. The ordinary NFA is able to get to, on input A, any of the states that can be reached using these transitions of the epsilon NFA on input A. That is, the ordinary NFA will have a transition from here to each of these states on input A. Now, since we don't close the states after a transition on A, we have to make additional final states, those that can reach a final state on epsilons only. So, for example, if this state might not be final, but it might be able to reach by epsilons some final state. If so, that is, this is a final state of the epsilon NFA, but in the ordinary NFA we're constructing, we're going to make this state be final. Because in effect, it has the power of a final state in the epsilon NFA. Whenever you get there, epsilons will take you to a final state, so you know that whatever got you here will be accepted by the epsilon NFA, so you want the ordinary NFA to accept it as well. We're going to start with an epsilon NFA that has the usual components, Q for states, sigma for inputs, and so on, but we'll use delta E for its transition function. Okay, and we're going to construct an ordinary NFA with the same set of states, same input symbols, same start state, a different set of final states, perhaps F prime, and its transition function will be called delta N. Okay, now, the way we compute delta N of Q and A is as follows. We're going to start in state Q. We're going to close Q, that is by following epsilon paths, to get to some set of states S. Okay, delta N of Q and A is take all the states in S, we find all their transitions on A, and this is the set of states that is delta sub N of Q and A. Okay, that is, in the ordinary automaton, Q gets you on A anywhere that the epsilon NFA can get you by following 0 or more epsilons, and then an A. Okay. Now, prime, the set of final states of the ordinary NFA, is the set of states Q such that the closure of Q contains a state of F. That's the thing that, again, allows you, if there's an epsilon path to a final state, then this state gets the same accepting power that wasn't needed in the epsilon NFA. Okay, we're not going to prove this, but the idea is that the NFA on any input W enters the set of states the epsilon NFA enters on the same input using epsilon transitions anywhere it likes except at the end after reading all the real inputs of W. However, state P in delta N of Q0 and W is a final state if in the epsilon NFA P can get to a final state following only epsilons. Okay. Thus, the fact that the equation holds, that is this equation here, is enough to say that W is accepted by either both or neither of the automata. That is, if delta E contains an accepting state, then delta N of Q0 and W will contain a state which has also been made accepting because it can reach on epsilons an accepting state of the epsilon NFA. Here's the epsilon NFA we used before as an example, and the NFA, ordinary NFA, that we construct. The interesting changes are marked in red. So first of all, here are all the non-trivial closures. That is, the closure of B, because B goes to D on epsilon, the closure of B is B and D. And the closure of E, which we've worked out before, is, E goes to B and C, B goes to D, so E can go to B, C, D, and E. Okay. In the NFA without epsilon transitions, we need to change the transition from E on input 1. And the reason is that we first take the closure of E, which of course is B, C, D, and E, and then we ask, where can I get to from those states on a 1? And if you look at the epsilon NFA from B, C, D, and E, all you can get to are C and D. Okay. So we put C and D. It becomes the entry there, whereas in the epsilon NFA it was the empty set. You can see that. Okay, the transition from E on 0 actually doesn't change. The reason is that B, C, and D have no transitions on 0. So the fact that we can get to them on epsilon doesn't help us when the input is a 0. Okay, finally, since the closures of B and E include the final state D, they become final states as well as D in the ordinary NFA. And that's the entire construction. So, we now have 3 different formalisms for describing languages: the DFA, the NFA, and the epsilon NFA. They look progressively more powerful, and in fact they are more powerful in the sense of the things they can do. But in fact they give us exactly the same class of regular languages. Very soon we'll see a 4th formalism called regular expressions that look quite different from these, but in fact also give us exactly the regular languages. So we might be getting the idea that the regular languages are quite a natural class of languages, and indeed they are. We should notice that the added power of NFAs and epsilon NFAs are quite useful. For example, we shall talk about designing automata to recognize sets of keywords, say the reserved words in C or some other programming language. That is an important task for building a compiler for the language. We could design a DFA for the task, but it's much easier to start with simple DFAs for each keyword. It's just a chain of states. Say for else, it's just an E, and L, and S, final state. Okay. So that's how you recognize your keyword else. Then we'll connect them all with epsilon transitions from a single start state. So you put an epsilon here. This becomes the start state. And you'll have epsilon transitions to a lot of these chains for all the keywords. And they, of course, all end in a final state. And that's all there is to it. You've got an epsilon NFA. And then we're going to convert them to a deterministic automaton, because the deterministic automaton is necessary for if you want to actually execute an automaton. That is, only a DFA can be implemented. No one has yet invented a non-deterministic computer, although I've heard that Intel is working on it.